Welcome to the video for C6.1.8, extracting aluminium. So before we start the new learning, we need to think back to previous learning. So way back in C3.3.1, we looked at redox reactions. We revisited this recently. We learnt the acronym OILRIG, which means oxidation is loss, reduction is gain, and we're talking about electrons. And in C6.1.6, which is only a couple of lessons ago, extracting metals, we learned that an ore is a rock or mineral that contains enough metal to make it economically worth extracting. And also that the way we decide the method for extracting metals is that we use carbon if the metal is less reactive than carbon, otherwise we use electrolysis. So our learning objectives for today are to describe how aluminium is extracted from aluminium oxide, explain why we use electrolysis to extract aluminium, and also write half equations. There's two videos here which are worth a look at. I've emailed those links to you in your weekly email, so you can click on those and watch those. They're worth a look. The RSC kind of shows the industrial process in action. The Few School kind of explains the theory behind a bit in the same way that I'm trying to do, but a bit more jazzy and professional. So extraction of aluminium, we need to look at the reactivity series here again. So you can see aluminium's just above carbon there. And because aluminium's above carbon, because it's more reactive than carbon, you cannot use carbon to reduce the aluminium oxide. So because we can't use reduction from carbon, it's not going to work. Then we need to use electrolysis, which we know is more expensive, but we don't have a choice. The other thing you need to know is you need to know the formula and the name of aluminium ore. So the most common aluminium ore that we use is aluminium oxide, and we call that bauxite. So before we look at the diagram of the process, we need to understand the main problem with the extraction of aluminium is, so when we think back to electrolysis, we should hopefully remember that we need an electrolyte, and that electrolyte needs to be a liquid. So it either needs to be melted if it's a solid, or it needs to be dissolved in something. And in the lab, we've mostly talked about it being dissolved in water. So we can't dissolve aluminium oxide in water because it's not soluble, and melting it is problematic because it's got a really high melting point, so we'd have to use lots of energy to melt it, and that's going to be expensive. It's also going to be really bad for the environment. So for both of those reasons, we want to reduce the amount of energy that we need to put in. So the solution to this, if you pardon the pun, is that we dissolve it in molten cryolite. So cryolite is a solid, but we can melt it, and it's got a lower melting point than aluminium oxide, so it doesn't require as much energy, so it's cheaper, it's better for the environment. And once we've got that melted, we can then dissolve the aluminium oxide in that. So we're using the cryolite as a solvent. So let's have a look at the diagram. So this looks a bit different to what you would normally expect electrolysis to look. If we think about our conventional diagram where you've just got, normally in the class, we've got a beaker with an electrolyte, and you've got two electrodes going into it. So it looks different. So we've still got a cathode and an anode, and hopefully we can remember, so we use the acronym PANIC, positive anode, negative is cathode. So the negative electrode is the cathode, and you can see here on this diagram, the cathode is the lining of the cell, and that's made of carbon. More specifically, it's made of graphite, because we know graphite is the allotrope of carbon that conducts electricity. So the anodes are also made of carbon, but they look a bit more conventional in that they're being dipped into the electrolyte like we would normally expect. But you can see there's 3 there, not 1, so that increases the surface area. There's more surface where the electrolysis can happen. So what else is on that diagram that we need to remember? So if you look, the electrolyte is our solution of aluminium oxide in molten cryolite. You can see, much like in the blast furnace, with a molten iron collection at the bottom, the molten aluminium collects at the bottom, and that's then siphoned off. Top right in the diagram is an important bit of text, which is that the carbon anodes need to be replaced very quickly. If you've watched the RSC video, you can see this happening. So the carbon anodes need to be replaced, and that's because you have oxygen being produced at the anode, and especially at those high temperatures, it reacts with the carbon to give carbon dioxide, and so that carbon, the amount of carbon there gradually reduces, so it needs to be replaced. So we need to know the half equations that happen in the electrolysis of aluminium. This is quite a common exam question. So at the cathode, we have reduction. Remember, reduction is gain of electrons. So the aluminium ions, the Al3 plus ions, gain free electrons to become aluminium. And at the anode, we have oxidation because we're losing electrons. You can tell that from the equation because the electron's on the right-hand side, whereas in the previous reduction of aluminium 3 plus ions, where it's gaining electrons, the electrons on the left-hand side. So at the anode, we have two O2 minuses reacting to give O2 and 4 electrons. And we can combine this to give an overall equation. And the overall equation is 2Al2O3 to give 4Al plus 3O2. Okay, that's the end of the video. That's all you need to know. See you next time. Thank you for listening.